Hello, welcome everybody. So we are starting chapter 11, and chapter 11 covers two types of reactions, substitution reactions and elimination reactions. That's actually broken down into 4 parts. So we're going to focus on the first part in this video, that's substitution reactions that are bimolecular, abbreviated SN2 reactions. So we're going to focus on the mechanism. I'm going to tell you a little bit about stereochemistry that comes out of that. And then reactivity. There are a lot of players that can really affect whether or not an SN2 reaction can occur at all. This can involve the nucleophile leaving group, the substrate, as well as the solvent. So this is just a little picture to just kind of give you a cartoon view of a substitution reaction. So you can have a group, say a halogen on an alkyl group, and that halogen can leave on its own and be substituted with something else, this little cat. Or you can have a halogen kicked out by another group, specifically a nucleophile. So we're going to explore a couple of those different scenarios. The main substrate that you guys are working with is an alkyl halide. This is sp3 hybridized, and you have a halogen off of it. The key feature is that because the halogen is electronegative, it makes that carbon electropositive. So it makes it more of an electrophilic carbon that will have a certain reactivity with nucleophiles or bases. Just a brief overview of substitution and elimination reactions. First of all, if you have an alkyl halide, you can undergo a substitution by introducing a nucleophile where the nucleophile replaces the halogen. This was what we saw with the kitty cats. Or you can have a base. A strong base, for example, hydroxide, can deprotonate a halogen here, kick out, sorry, not a halogen, sorry, can deprotonate a hydrogen here and kick out a halogen to give you the alkene elimination product. So what's really tricky in this section is knowing what's going to happen. Are you going to get substitution? Are you going to get elimination? Maybe you're going to get both. Sometimes it is hard to control the types of reaction and their products. So at the end of each section, I give a summary, and that's what you really want to focus on and just key in on what you need to have a substitution occur. What conditions usually give elimination? So for example, if I use sodium hydroxide, that can act as both a base and a nucleophile. If I have the secondary alkyl chloride, I could get the elimination product, or I could get the substitution product. So this is where it gets tricky. Sometimes you get both. Sometimes you can modify the substrate or the nucleophile to give you one or the other. Just in general, I think you guys have a feel for this already. Alkanes are the least reactive of organic compounds. There's no handle there. It's just hydrocarbons, no dipole. Adding a halogen definitely creates a more reactive carbon center. And the reason is, again, you create this dipole, you get this electropositive carbon, which can act as an electrophile. A nucleophile can come in and attack here. So that's one of the ways. The other thing is that halogens themselves, they're very good leaving groups, meaning they could just leave on its own like that cat. And the reason is halogens are, especially as you get further down on the periodic table, they're very polarizable. They can handle that negative charge. For the same reason why HCl is a strong acid. That conjugate base, Cl minus, is very stabilized. That chlorine can handle that negative charge well. It's very electronegative, and it's okay being on its own. So certain substrates, the halogen will leave on its own, and you can either have a substitution or elimination. But a good leaving group is important for these reactions in this section. So here are some good leaving groups. These are conjugate bases of strong acids. The reason is that if you have a strong acid, that means that conjugate base is stabilized. So it's happy being on its own. So here's just a table of pK values. Just to remind you, we have the lower pK up top, which means you have the strongest acids. So you have HI, hydriodic acid, HBr, HCl. This is toluene sulfonic acid. This is really good because the conjugate base is stabilized by resonance as well as a negative charge on the electronegative O, hydronium ion, etc. And you guys can take a look. Just remember, down here are things like NH, very high pKa. Also, alkanes have a pKa in the 50s. So just to calibrate you there. The corresponding conjugate bases are shown here. These are the good leaving groups. Recognize these. These are I minus, Br minus, Cl minus. This is from the toluene sulfonic acid. So we call this a tosylate or a TSO group. A tosyl group is sometimes what it's called too. But basically the formal name is tosylate with the O minus. Water is a good leaving group. So just to be clear, if you have like an OH on its own, hydroxide is not a good leaving group because it's negatively charged. All that positive charge is on that O, but there's no resonance. But if you could get water to be a good leaving group, meaning you protonate an OH or OH2, then you basically have something that's in the same category of pretty souped up leaving groups. So these are the leaving groups that we'll be seeing more of in this section. The other thing I want to mention is just the way the language we use. So if you have an alkyl halide here, the carbon that's directly attached to the halide is the alpha carbon. The next position over are beta carbons. This is just easier. This is just easier to just identify. For example, if you need to do an elimination, you eliminate a beta hydrogen here. Okay, the other thing is you can have primary, secondary, or tertiary alkyl halides. A primary is where you have a carbon attached to another carbon. So the halogen is directly attached to carbon, attached to another carbon. For secondary, the halogen is attached to carbon, attached to two carbons. So R is just a generic alkyl group. Here, the carbon attached to the halogen is attached to 3. So this is important because these will have different reactivities. I mentioned that there are 2 different types here of substitution reactions, and these are based on their mechanisms. The first is based on a concerted mechanism. Concerted means happening simultaneously. So what happens is you have a nucleophile in your substitution reaction, and it's going to attack your substrate and kick out the leaving group. All of that happens at the same time. That's the concerted mechanism to give you your substitution product, where now the nucleophile replaced the halogen. We call this SN2. The next mechanism is stepwise. This is where having a good leaving group and having a substrate that can stabilize the carbocation is good for this pathway. So basically, in the first step, your leaving group leaves to give the free carbocation and your halide or your tosylate. This is a completely different mechanism than the SN2. The SN2, you don't involve a carbocation. Here you're generating a free carbocation that's going to be, in this case, that would be sp2 hybridized, it's planar. And then your nucleophile can attach to give your substitution product. This is SN1. It's unimolecular versus bimolecular. So hopefully you can see this is really important to know which type of mechanism is going to be operative, because clearly that's going to affect stereochemistry. So today I'm just going to focus on SN2 reactions: substitution, nucleophilic, bimolecular. Concerted, this happens all at one time, the same time, simultaneously, to give your product. It's bimolecular with a second ordered rate law, meaning the rate is dependent on the concentration of the alkyl halide as well as the concentration of the nucleophile, because both need to be present, both are interacting, both are present in the transition state and kick out the leaving group. Overall stereochemistry occurs with inversion. So your nucleophile, which is SH minus here, is going to attack from the back side and kick out bromide. That occurs with inversion. Think of an umbrella flipping inside out. So for example, here we had S, here we have R. And the reason it occurs with inversion is because of this backside attack. You will attack from this side, you get your umbrella inversion, and then the bromide kicks out. There are two reasons for this backside attack. First of all, you have this leaving group. This is going to develop a partial negative charge. So think of this as high electron density here. Your nucleophile is likely going to have a negative charge or very strongly partial negative. So there's repulsion if it comes in from the front side. So it does want to prefer to come in from the back. The other thing that is, if you're interested in, I'm not going to test you on any detail of this, but it involves specific orbitals. So back when we started the semester, we talked about molecular orbitals, antibonding and bonding. But basically, the way that the chemistry works in terms of organic chemistry, a nucleophile coming in reacting with an electrophile, it's the HOMO, which stands for the highest occupied molecular orbital of the nucleophile, is coming in. So basically it's electrons in this occupied molecular orbital are going to react with an available unoccupied molecular orbital, and it's just a lower lying one. So for your alkyl halide, it looks like this. This is your LUMO, your lowest unoccupied molecular orbital, and basically it's going to interact with this lobe here. So backside attack allows you to attack here. Front side attack would have been blocked because you have this node here as well. So you could think of it as both ways. This electron density and the repulsion doesn't want to come here on the front side, and then the node here for front side attack as well. Okay, what will really help you envision how the stereochemistry is created is this transition state. Backside attack goes through this transition state. So you should be able to draw this. You're starting to break the carbon halide bond, dash, dash, dash. And you're starting to form the sulfur carbon bond, dash, dash, dash. What's in between is just this planar carbon that has three groups. So think of this section as trigonal planar. But when you have these two guys here, which if you flip on its side is axial, this is a trigonal bipyramidal geometry. Some of you have learned that in general chemistry. But basically, this is your key transition state. Notice the transition state symbol. So this is kind of halfway through that umbrella inversion. And as the bromide finally leaves, the sulfur is on this end creating and recreating that tetrahedral geometry shown here. So overall, this transition state explains this inversion of configuration because everything is still connected and it's concerted, meaning you don't have a free carbocation and the nucleophile can't attack from equal probability from the front or the back. So this is a stereospecific reaction because of this backside attack and this concerted mechanism. Look at this energy diagram that also shows this. Here, this example is using cyanide as a nucleophile. So if you start here, this is your starting point of starting materials. You got to climb this hill. That's your activation energy. At the top, at the maxima, is your transition state. That's the hardest thing to do. Look at this transition state. This is tricky. You're asking two molecules to come together. So you're fighting entropy and you're starting to form bond and break bonds. So that's the peak. Once you get here, you could go downhill, form your substitution product. Think about what sort of effect the substrate can have on the rate. If this is your rate determining step, this is the hardest thing to form, what would make it harder? What would make it easier? Just to give you a clue, this is really dense. You're bringing in some molecules together in this specific space. So have a think about why certain substrates might be better than others. So I alluded to it, it's a tight space. So basically, if you have more bulk on your substrate, it's harder for this to organize. So if we had just on the previous slide a certain activation energy for this methyl substrate, methyl bromide, that occurs with a certain energy, what if I have a primary halide then, where I have this extra methyl group? The cyanide needs to come in to a more bulkier situation, so there's more sterics, that'll require a little bit more energy. A secondary substrate, that'll require more activation energy. So substrate does play a role. Tertiary is so high in energy because there's so much bulk and you're trying to get this nucleophile in here. It's extremely slow. Basically, we call it unreactive. So this is a reactivity. Tertiary is unreactive. Secondary is better than that, but primary is pretty good. And the most reactive is methyl, a methyl halide. Okay, so I can actually show this just by showing you rates. So this is the exact same concept. I'm actually starting with an alkyl bromide, and my nucleophile is iodide. Iodide is actually a better nucleophile because it's more polarizable. It's going to come in and replace the bromine. So here is the ethyl bromide situation that we were just talking about. I'm going to let that be our baseline of 1. If I used methyl bromide, the rate is 145 times faster. If I use a secondary bromide, that's quite a bit slower, and then tertiary is negligible. If I put the branching further out at the beta position, it's still harder to do, but it doesn't have the same effect. So meaning if I put a methyl group at the beta position, my rate isn't that much more diminished from just the ethyl bromide. The secondary not as bad as what we saw over here, but still the tertiary is pretty bad. Okay, just to practice, I want you guys to draw the transition state for the following SN2 reaction. So just to remind you, that's a trigonal bipyramidal transition state. So pause this and draw that out, and then I'll go over it. Okay, so you should have come up with something like this. I put the alkyl group up, but it doesn't matter. Basically, this section here is your substrate. That's trigonal planar because it goes through this trigonal bipyramidal, basically kind of 2 pyramids, if you want to think of it that way, transition state. You should have this double dagger here to show it's in transition state. Also, you're starting to break the CCl bond, starting to form the OC bond. Your nucleophile is OH minus, so overall that is a negative charge, but when it starts to form the bond, it's partial negative, and then as Cl is starting to leave, it's partial negative as well. There is no partial positive. Eventually, you're going to get Cl minus, which can be balanced out with the Na plus, and overall, the alcohol product. Okay, we're going to talk about effects of nucleophile leaving group and solvent, and then you guys will practice. So you want a strong nucleophile. Ideally, it's negatively charged. This will go fast, like a hydroxide coming in, kicking out iodide to give the alcohol. If it's not negatively charged and neutral like water, that's a lot weaker, and it's going to happen quite a bit slower to give this, and then you can do a proton transfer to give your desired alcohol product. So what makes a good nucleophile? Basically a really strong nucleophile being negatively charged. That's usually better. This tracks with basicity. And as the electron density increases, nucleophilicity increases. So these negatively charged nucleophiles are better than their neutral counterparts, shown here. The other thing is electronegativity. you want your nucleophile to not be as electronegative, because more electronegative means it's holding on to its electrons more, or holding on to that electron density more. So the more to the left on the periodic table is better. So CH3 minus is better than NH2 minus, all the way to F minus. That's the worst in this range. That goes for the neutral nucleophiles as well. Polarizability is better. So that's why I was saying I minus will kick out Br minus. As you go down the periodic table, I minus is more polarizable. It's got more shells, more electron density, so it's more nucleophilic. Same thing as you go down group 6. Selenium's better than oxygen as a nucleophile. P is better than N. So again, it's just they have more diffuse and polarizable electron clouds. And essentially what that's allowing is orbitals can better overlap when you're in that transition state. The other thing is, and we've already touched on this, steric hindrance. You want less bulky nucleophiles. These are better. So just the methoxide is better than tert-butoxide. And it's just because the smaller guys can get into that transition state, get organized in that transition state easier than something bulky that has a little bit more or a lot more steric hindrance. Leaving groups that are better stabilized are to the negative charge are better. So tosyl, or the tosylate here, is better than iodide, which is still very, very good. Bromide is still pretty good. And then it drops off with chloride and fluoride. And then these hydroxides, already mentioned, these are poor leaving groups. They don't have any real stabilizing factors. The last thing I want to mention is solvent effects. So basically, you want a polar solvent. You guys have already seen, for example, in certain reactions, you use carbon tetrachloride that has polarity to it. But there's something else that we're going to talk about. You can have polar, but some are protic and some are aprotic. So protic means you have a hydrogen attached to an electronegative atom. So that can lend itself to hydrogen bonding. Very strong plus minus ends. Aprotic doesn't have hydrogen. So think of prot as proton. Aprotic is without proton attached to an electronegative atom. So that would be something like acetone or DMSO, dimethyl sulfoxide, DMF, acetonitrile. These have electronegative atoms, but no H is directly attached. So they can impart a partial negative charge. So these, though, the protic solvents, they can have a plus or minus. This has a big effect on solvation of your nucleophiles. So in a polar protic, such as water, you have a plus and minus end. So here's a plus end of water's H, and it can interact, and it can actually stabilize your nucleophile or your anion. What that does is it lowers the energy and makes it less reactive. So this is actually not good. This is going to tie up your nucleophile. If you have an aprotic solvent that can only give like partial negative, it can solvate the cation, but it won't have that plus end, that kind of more hydrogen bonding HN to solvate the nucleophile here, chloride. So what ends up happening is your nucleophile, or Cl minus here, is not stabilized, so it's higher in energy and it's actually more reactive. So if you want the SN2 to go, that's actually better, because that means in the polar aprotic, your chloride is higher in energy here. It's not stabilized down here. So look, it's closer to the transition state, which means it has a lower hill to climb. Your activation energy is lower. So for SN2 reactions, the take home is aprotic solvents are best. And it's just because in a protic solvent, those nucleophiles are more stabilized and lower down, so it causes a greater hill to climb. And in an aprotic solvent, those nucleophiles are higher in energy and more reactive, lower hill. Okay, So our summary here is just don't forget the big picture. What are you actually making? Our business is organic synthesis. So you're taking an alkyl halide and you can alkylate something. I have a nucleophile. It can be a variety of things, a carbon nucleophile, a sulfur, oxygen, etc. But basically, you are alkylating something. You're adding an alkyl group to this nucleophile. Some notes for a better SN2 reaction, just keep in mind what that transition state looks like. It's organized, it's tight. You need both of them, both the substrate and the nucleophile to get organized. So less bulky is better, a less bulky substrate and a less bulky nucleophile. Also, you need a strong nucleophile. Strong is negatively charged. Those are the key features here. A better leaving group helps you as well, and you want a polar aprotic solvent. Okay, let's practice 3 problems. So read these, pause, and then spend some time working on these. Be thoughtful with these, and then unpause and I'll go over it. Okay, so the first one, why won't the following occur? I have a secondary alkyl bromide, and I'm trying to react with potassium tert-butoxide to give this ether product. Why doesn't this occur? It's because the nucleophile is just simply too bulky. If it tries to go into that transition state, there is just too much steric hindrance, so it's not really going to get in there and form and go through that trigonal bipyramidal transition state. What likely occurs in this situation is an elimination. You deprotonate an H here, and you kick out bromide, form a double bond. Okay, the second one is which will react faster in an SN2 reaction with sodium hydroxide. So here I have 2 methyl halides, one with a chlorine leaving group, one with an iodine leaving group. So the methyl iodide will react faster. The reason is iodide is more polarizable. It's happier as I minus versus Cl minus. I minus is a better leaving group. The only one better that I showed you so far was the tosylate. For this next one, this methyl chloride will react faster than the tert-butyl chloride. And for a similar reason as our first problem, it's just too bulky. The tert-butyl is too bulky. You want the less bulky substrate is going to react faster because you can organize that transition state better. There's less steric hindrance. So methyl chloride is going to react faster. And then predicting this product, CN is your nucleophile. It's going to come in. So you have a small nucleophile. I didn't give the solvent, but you could use any aprotic solvent. It's going to react here. You can go through this trigonal bipyramidal transition state, and it's going to kick out bromide. Again, that's a concerted reaction mechanism for SN2. Overall, you've replaced the bromine with CN. I drew CN out. Cyanide is carbon triply bonded to nitrogen. And just remember, you have a carbon here. If this is hard to visualize, just write out the carbon when you do your work. But basically, do the framework first. 1, 2, 3, 4. 1, 2, 3, 4. So you have your butyl framework, and then you added another carbon from the CN and the rest of that. Okay, this is where I'm going to end, and we will continue more with SN1 reactions next time, and then we'll talk about eliminations.